Welcome to this Coins 2020 presentation. My name is Taner Özçelebi. I'm an associate professor at Eindhoven University of Technology at the Department of Mathematics and Computer Science. Within the department, I'm working in the System Architecture and Networking Research Group, which specializes on resource-constrained network-embedded systems. My own research is focused on intelligent environments of resource-constrained network-embedded systems and, you could say, intelligent Internet of Things. When we talk about intelligence, of course, we need to talk about sensing. Today, I'm going to talk about multi-sensor sensing specifically, and I'm going to present our work on automated data augmentation for robust multi-sensor sensing. My collaborators in this work are Atip Said, a PhD student of mine, Ye Li, she was a master's student of mine who already graduated, and Professor Dr. Johan Lukin, with whom we did this work. Let me try to put our work into perspective. As most people are well aware, deep neural networks are getting a lot of attention from the research community and from the tech industry as an artificial intelligence solution to many problems ranging from surveillance to healthcare to automotive to intelligent lighting. And there are various success contributors to Dnns. First one is perhaps that what we can call the algorithms or models. Defining a suitable architecture of the DNN is central to its performance, of course. Clearly, DNNs are quite hungry for computational power as well. And last but not least, we need data. We need massive amounts of well-curated data to train DNN models that perform well and that generalize well. Sometimes getting our hands on such massive data is possible, as in the case of online image repositories and as in the case of, let's say, Tesla cars continuously collecting data that are used to update an assistant driving model. But sometimes collecting such data is simply not doable, at least not doable very easily. What do we do then? In this case, just give up? Of course not. We have to find a way to make better use of the data that we have. Data augmentation is a way to synthetically generate more data, typically by applying transformations on the authentic data. Such transformations are by design output invariant. So what this means is, for example, in the case of classification problems, these transformations, when applied on input data, should not change the resulting output label. The two photos that you see on this slide are essentially the same. In both photos, it is me posing to a camera in front of some Dutch landscape and a beautiful windmill. There's only one difference though. The photos are horizontally flipped versions of each other. If you show them to different people that know me, they will all say that it's me in the photo in front of a windmill. The horizontal flip is merely an insignificant detail here. It has no semantical meaning in this context. So why do we want to augment more data in this way or in similar ways? The advantage of data augmentation is when we train our DNN models with a combination of original data and augmented data, our models can generalize better and they can perform better on any test data they are evaluated upon. Data augmentation is well covered in the literature. However, data augmentation on time series data has been studied by very few papers in the literature. The state-of-the-art mainly focuses on a limited number of transformations, namely adding noise to the input, warping the signal, and integrating discriminatory factors based on some prior knowledge. This means that there's a lot of potential for improving the performance of multi-sensor sensing by designing automated selection of data augmentation strategies and by expanding the search space, for example, by designing novel transformations. In this work, we propose exactly that. We propose what we call Sensor Augment, which is a general and flexible framework for automatic discovery of data-specific augmentation strategies. And the framework starts from a rich set of user-defined transformations and selects an optimal subset of these along with their optimal parameter settings. In this case, optimal means that the selected subset of transformations and their parameters settings give the best performance on a variety of tasks. As I will explain later, we're going to assume a fixed network architecture, and we're going to use a black box optimization style for this purpose. Namely, we're going to use evolutionary search algorithms. Regarding automatic determination of the data augmentation strategy, and I'm talking here about any type of data, not just multi-sensor time series data, well-known approaches in the literature can be divided into two categories. The first category utilizes generative models like generative adversarial networks. The second category tries to learn its strategy directly from the dataset, discovering data-specific augmentations in a black box manner. So no involvement of a domain expert is there. Note that the transformations applied here need to be suitable for the considered data sets. For example, if we're talking about image classification, then we also expect to see image transformations. That means different types of data require different sets of transformations. Considering all this, there's a lot of work to be done in the domain of multi-sensor time series data and a lot of questions to be answered. Questions like, are there transformation alternatives to noise and warping, and these need to be label invariant? Does a particular transformation preserve the class label? Which transformation operations can be reused across a variety of time series data? What is the optimal range of parameters for different augmentation functions? How to deal with heterogeneous multi-sensor inputs? So these are all relevant questions that we need to answer. Overall, our paper provides the following contributions. We provide a framework for automatic discovery of optimal augmentation strategies for multiple sensor time series data. This is called the sensor augment framework. Secondly, we introduce a new label we introduce a new set of label invariant transformations for multi-sensor time series data. Thirdly, we implement evolutionary search algorithms for finding the best augmentation strategies. And finally, we make an extensive analysis to determine the feasibility of the proposed technique across a diverse set of problems and datasets. We test its effectiveness under a low data regime and on the transfer of the learned strategies between related tasks. Our experiments show actually a performance gain between 1.5 to 10% increase in F-score on top of the baseline, which is ordinary supervised learning with no augmentation. The picture here depicts the sensor augment framework. We start from a search space that consists of available transformations that are user-defined. The black box search module is the one that is responsible for creating a repository of augmentation strategies from which an augmentator can create additional data by transforming the training samples that come from the multi-sensor dataset. The data are then used to train a network whose performance is evaluated on a validation set. The F-score on the validation set is fed back to the search module, which uses this information in updating its strategy repository in an iterative fashion. The transformations under consideration in this work are listed on this slide. The ones on the left, namely blend, shuffle, shift, flip, and mask, are the ones that we found are used in the literature, while the ones on the right, namely noise, scale, rotate, time warp, permute, and magnitude warp, are our own designs. Let's talk about these transformations in more detail. The table here shows the magnitude parameters of each transformation and the considered range of their values. So those are the parameter search space, basically, that need to be searched through, and we need to optimize to find the best set of transformations and their parameters. Scale is referring to randomly rescaling the magnitude of all the samples within a window. a time window. Noise adds random noise to the input. Time warp would distort time intervals between consequent input values. Magnitude warp, in this case, the output is a convolution of the input with a randomly generated window of noise. Rotate actually just applies a random rotation to the input, changes its orientation. Permute swaps different slices of the time series in a window. Shuffle would, for example, shuffle the dimensions of a triaxial accelerometer sensor. Shifts the samples in a window to the right, so samples at the end would roll back to the beginning, representing a temporal translation. Flip would reverse the input horizontally along the time axis or vertically along the sensor value axis, and mask would randomly mask the consecutive samples with zeros, simulating missing data. And blend gives a linear combination of an instance with another of the same class. In the optimization process, we are in search of an n-dimensional vector describing a set of augmentations and their augmentation parameter settings for each sensor input. As I mentioned briefly in our work, we utilize evolution-based optimization algorithms for this, which I also called sometimes black box algorithms in previous slides. The three types of algorithms that we tested with our random search, particle swarm optimization, covariance matrix adaptation evaluation strategy. The optimization works as shown in this algorithm. To summarize, we have a training set and we have a validation set, and we have an evolution-based search and optimization procedure that we can call E, and we have a search budget that we can call GB as input to this algorithm, and in every iteration we randomly initialize the deep network and select an augmentation strategy proposal that we may call P, capital P, from the search space. And we do this using the search procedure E. The top n subscript P highest scoring strategies among those after the search budget is consumed fully is output as the set of optimal strategies. This is the algorithm. So note that for each input modality, a different strategy P will be searched by the search procedure E. So for each input modality, we have then we can find the optimal set of translations. Our Dnn architecture consists of multiple streams, each with a learning module to capture the unique characteristics of the corresponding modality. Each stream has 3 convolutional layers with 32, 64, 96 units, followed by max pooling and dropout layers. The outputs of these streams are fed to a shared network where they are concatenated and then further fed into a 1D convolutional layer with 128 units. The output of that is then fed to a convolutional layer with number of channels equal to the number of classes or the number of regression outputs. Then we apply pooling. For a classification task, we also apply a softmax filter to get the class probabilities. More details about the network can be found in the paper. For now, I would like to explain it so far. We tested on a diverse set of data sets. This includes 4 data sets with activity recognition as the end task, namely HHAR, MobiAct, MotionSense, and HAPT. These datasets differ significantly in the number of users that participated and the number of activity classes. We also tested on 3 more datasets, one on heart rate estimation, one on sleep stage scoring, and another one on stress detection of the driver in a car using heart rate and skin conductance as input. The activity recognition datasets made use of other sensors like accelerometers and gyroscopes. Likewise, the heart rate estimation and sleep stage scoring employed different types of sensors as well. So this variety makes this collection of dataset quite diverse, which is very suitable for our testing purposes. Here are some results over 10 independent runs of model training from scratch. Here we compare the F-score and kappa performance of the proposed framework against the baseline, which is, as I said, standard supervised learning without augmentation. In the last three columns, you see the performance of the proposed framework using different evolutionary search algorithms, namely random search, particle swarm, optimization, and covariance matrix adaptation evolution strategy. Here are the results of transferring augmentation strategies on the activity recognition task. The optimal augmentation strategy from each dataset is used without modification to learn a model on a different one. The results show that the strategies transfer actually very well and result in performance that is better than the baseline. The figure shows the performance in a low data regime. The best augmentation strategies found on each activity recognition dataset are used to learn a model with few labeled instances per class on another dataset. The results are dramatically better than what the baseline can do again. With so few labeled samples, especially, it's quite impressive. It is as if the network is trained with a very large dataset in a supervised way and not like in a low data regime. In summary, the proposed sensor Augment framework is a generic and flexible framework for automated learning of augmentation strategies. We also proposed the new transformations that are label invariant that can be used in multi-sensor time series settings. We use evolutionary search algorithms to find an optimal strategy for augmentation for multi-sensor tasks, and we showed that learned strategies transfer well between different data sets as well. We significantly improved performance on a diverse set of tasks and data sets, and we also showed this impressive improvement of performance in a low data regime as well. Further challenges for the future are joint optimization of network architecture design with the augmentation strategy and finding a unified scheme that is applicable to multi-sensor data. Thank you for your time. This project was funded by the Scott project, Secure, Connected, Trustable Things. It's an Excel project of the European Union. For your questions, you can always email me or any of the other co-authors and expect an answer. Thank you very much.